Hello, everybody. I'm Paul Ezekiel, and I'm going to give you a talk on climate variability of atmospheric rivers and droughts over the west coast of the United States from 2006 to 2019. So first of all, I'm going to show an outline of what we plan to talk about in this discussion. I'm going to talk about research objectives first, then come down into the methodology, uh, what are the cosmic vertical profiles, how did we use them, and then regional climate characteristics, what data sets we used, etc. Go into the results, then talk about conclusion and final remarks, then go into some future work and present work that I'm actually doing right now, give some acknowledgments, and there's supplementary resources and references at the end of this talk. So first of all, I like to talk about our research objectives. So our main objective when we developed this experiment was to perform a comprehensive study about the attributes and factors that led to droughts and atmospheric rivers. So we plan to look at precipitation events and droughts during the wet season of California from 2006 to 2019. If you are not familiar what the wet season of California is, it's about October to about March, maybe into April. And that varies each year, but we're looking pretty much into those months. And the other objective with it was discern if the strength of ARs are increasing from previous years and the variability of droughts, understanding of how climate has changed and maybe what underlying factors are causing them to increase or become more frequent. Our hypothesis was cosmic vertical profiles will actually provide more insight into why the West Coast was seeing an extreme drought, which actually occurs from 2012 to 2014. It was the third driest in recorded history, and then followed by an extreme atmospheric river event year in 16 and 17. And we figured cosmic would be able to give a full idea, a good backstory of kind of how these factors and what has to be there in order for one of the two options, one of the two extremes to occur. So we'll look at methodology. So this is the cosmic vertical profiles. So we use the wet profile. There's a variety of profiles you can use. We wanted to look at the moisture, so we looked at the wet profile. We use profile heights from 0 to 5 kilometers. A lot parts of my talk, I'm going to talk about the 0 to 5. That's kind of what we're taking. We're taking what the lowest value is from the surface up to 5 kilometers and taking the average of the profile. As you can see in this figure on the bottom right, or bottom left, sorry. And what we did was we plotted of the variables that we get from the instrument itself. You get pressure, you get temperature, you get vapor pressure. But what we didn't want to just look at vapor pressure itself, we wanted to actually calculate what's the mixing ratio. So we use this formula to calculate mixing ratio and to put it in grams per kilogram. We researched between the start of the mission, which was in June of 2006, and we ended the mission basically right at the point the instrument went offline. We did exclude the last couple months of data due to tons of errors, a lot of missing data as the satellite was losing the ability to update data to it. So basically went through the entire lifespan of Cosmic 1, and we focus our domain in the Pacific Northwest and down at the edge of southern border of California. So 30 north to 50 north, and then 140 west to 120 west, as you can see in the figure right here. So when we're going to talk about the regional climate characteristics, we used a variety of data sets. The first one we used was the NCEP NCAR reanalysis data. We used that to characterize what the 500 hectopascal geopotential height and the 1,000 to 500 hectopascal thickness anomalies were. And all anomalies that we were creating in this study right here were basically taking data from 1989 to 2020, and then comparing what the seasonality of it is, using like the autumn months as in sun, September, October, November, and then DJF or December, January, February for winter. So the next one we used was the NASA JPL Making Earth System Data Records for Use in Research Environments, the measures to evaluate sea surface height variations over the target area. Measures provides about a 0.17 by 0.17 degree analysis data set with 5-day temporal resolution of sea surface height and sea surface height anomalies. They're basically from a set of quite a few instruments, the Topex, Poseidon, Jason 1, Jason 2, Jason 3, with the ERS 1, ERS 2, Invisat, Altica, Cryosat 2, and the Centennial 3A. You put all those instruments together and the satellites, and you get basically the sea surface height variations. The next one we used was the NOAA National Data Buoy Center, or NDBC. We wanted to see what the buoy temperature was in a variety of locations, so we used those just in order to get some in situ observations. NOAA, a 1/4 degree daily optimum interpolation sea surface temperature version 2. We use that to get sea surface temperatures. And basically, the optimum interpolation is just constructed by combining observations from different platforms, use satellite, ships, buoy data, and Argo floats. So another, just kind of seeing what the temperature field would be looking like, especially in the ocean itself. And then the final one, we use National Weather Service range gauges. We were planning to actually start off with using satellite data, but because of the complex terrain in the Pacific Northwest and in California itself, we saw a lot of discrepancies between errors with resolution, missing higher terrain locations, over predicting in lower terrain locations. So we just ended up using rain gauges for analysis for that. All right, so we're going to focus now into the results. So this right here is a cosmic time series. The first thing I like to denote is that we have we're looking at the monthly averages and the seasonality of mixing ratio. So what we actually notice is there's a decreasing trend in mixing ratio at the very beginning of cosmic from 2006 down really to 2012 into 2013, right at the beginning of 2013. What's analogous is that in 2012 to 2014, as I said earlier, this is when we had the extreme drought. So making general sense of the mean annual mixing ratio as that's dropping makes pretty good sense. What was interesting is how it flips in 2013 and starts rising. And we'll be able to explain that later with sea surface temperatures and sea level heights. And then it increases 16 into 17. You see the strongest increase. That was the steepest climb of the entire data set of 0.32 grams per kilogram. And it topped off at 2.8 grams per kilogram. In 2018, right after that active rain year of 17, we actually saw another year of below average precipitation. And you'll see that in the mixing ratio, it actually dipped by about 0.2 grams per kilogram in that 1 year. So to further analyze what's kind of going on here, we're just focused on autumn or October to March. We created a heat map here. So our plan was to look at what the normalization of this data set is and anomalies, just to kind of get an idea if there's any patterns that we see. What we observed was that there's this possible sinusoidal pattern and wave pattern right here. If you look at just the color scheme in this heat map. So we'll move on to the temperature field. We saw similar results as we did in the mixing ratio. We saw a decrease in temperature from 2006 to 2013, just like we saw mixing ratio. Stabilizes in 13, starts increasing. One interesting fact was buoy data, which is what you see on the left here. They had temperatures maxing in these 8 locations in 2014 into 2015, but the cosmic profile average actually measured the highest temperatures in 2016, which kind of matches with the data that was set by NASA. Phillips and Leslie said in 2016, global average temperatures witnessed the warmest year in the last 137 years of recorded data. So the cosmic profile actually matched that data. Getting into beginning part of the regional analysis. So what we noticed was looking at autumn and winter months between 2006 and 2011, what we saw is the Western United States observed oscillating weak, positive, and negative height and thickness anomalies. You'll see these here. They're offsetting. In 2012, as the drought began, you'll actually see a predominant red zone here, or a ridge that pops into the west coast, and that persisted. What we actually was denoted the ridiculous resilient ridge, or the triple R. That stayed around for a few years. So basically, that was why in those years the drought conditions were met. That ridge just kept taking more offshore winds during those years. And then the pattern shifted into 2015 as the trough started making an eastward push. And you can see that, especially in 16 and 17, in December, January, February, that eastward push right into the Pacific Northwest that allowed the flow around that low pressure to tap into the moisture field upstream and into the tropics, and allowing more atmospheric rivers to propagate into the area. As you can see, 17-18, that return of a ridge, and 18-19, we saw another decent rain year, and that trough came back. In terms of sea level heights, we're going to focus mainly on that during the first 8 years. Overall, it looked pretty cool. Temperatures on these anomalies fluctuated, positive and negative, but you really see a big influence in 13, 14, and 15, and that's because of the drought and the high of the ridge. Due to the lack of convection, more radiation was getting down to the surface, allowing for more evaporation, So that allowed also the ocean surface to warm up. 16, 17, you can see in December, January, February, there's this cool water pool here. That is associated with just all the storm tracks that came through here during that set of few months. And we want to actually look at what the yearly percentage change was in the 4 quadrants. So what we did was we took the domain and broke it down into 4 subdomains, and you can see that in a time series here. That the heights, you can see that it's pretty stable, drops in right at the beginning of 12, and then rises all the way through the drought, and you can see a decrease in all 4 locations during the rain year. Percentage differences, this basically goes analogous with the ENSO. We'll see that in the next slide. We'll be talking about how the ENSO kind of oscillates between the two, and that's how these percentage differences kind of go. When we look at the sea surface temperatures, very similar pattern, positive and negatives, anomalies in the first 8 years, that warm push of warm water that associated with the El Nino. And then we had a La Nina in 16, 17. Linear regression, I'd like to look at two things. We looked at sea surface temperature versus sea level height anomalies, and we found actually the linear regression actually had a 0.5 R squared value. So then we were looking at, okay, if those two are related, as with the expansion and compression of the ocean water due to the heating or cooling, how much does that influence the mixing ratio? So we took the height field and looked the height field as the sea level height and compared it with the mixing ratio for cosmic, and you got a 0.65 regression coefficient. And then just finalizing on the atmospheric rivers and precipitation, we looked at how many total number of landfalling atmospheric storms occurred from 2016. And then in 16, we had our big atmospheric river event year. We had 50 total. Predominantly, most of the atmospheric rivers found themselves in the northern California to Oregon up into Washington. And then in 17, 18, we saw a dramatic drop-off as another ridge came in. But still location-wise, they stayed around about the same, predominantly up north. In 18, 19, the atmospheric rivers increased, and Northern California and Oregon also saw the most. However, 1920, which is after this study, really, we're looking at just the concept of it, that ridge actually will pop back in 19 and 20 and push those storms further north. And that didn't allow the storm track to come as far south as it did in the other 3 years. If you look at the precipitation field itself, we kind of see that similar like sinusoidal type of pattern here. Rising total amount of precipitation in the first 5 years, decrease, of course, during the drought, another increase, peaking in 16, 17, and decreasing through these 5 locations. So just conclusions and final remarks. Mixing ratios, what we saw was a slight decreasing trend of 0.19 grams per kilogram from July 2006 to early 2013. Late 2015 to 2016, mixing ratio saw the steepest climb, 0.32 grams per kilogram. 16-17, the mixing ratio peaked and stayed constant at 2.8 grams per kilogram. So we say that the moisture increases in the atmosphere, the total frequency and strength of atmospheric rivers could potentially increase. 2018 mixing ratios dipped by 0.2 grams per kilogram, stay constant through the rest of the study period. In terms of the temperature field, 06 to 13, similar decreasing trend, about 2 degrees C. Buoy temperatures in 14-15 saw the highest temperatures. However, cosmic temperature profiles agreed with the warmest temperatures in 2016. The cosmic heat map showed a possible sinusoidal wave-like pattern between the October and March plot. And similar sinusoidal wave-like patterns are actually found in annual precipitation and sea level height anomaly fields. And then finally, SLH anomalies with the cosmic mixing ratio produced an R² of 0.65. We said that because SLH increased due to enhanced warming during the drought, consequently increasing evaporation and providing more vapor to the atmosphere. SLH anomalies with SST anomalies produce an R² of 0.5. Since the SST lagged behind the seasonal air temperature due to the high specific heat capacity of water, it appears that having a warmer summer and autumn can allow more moisture to be lofted in the atmosphere for the following rain season. And SST directly affects the location of the mid-level trough and a ridge, as seen in the Jupiter height and thickness fields. Droughts observed cooler SSTs, consequently leading to a persistent 500 hectopascal ridge. And during active rain seasons, we actually see warmer SSTs, and that allowed the 500 hectopascal trough to push eastward toward the Pacific Northwest. So some future work is we're creating a similar experiment design and moving the domain around to see if we see the similar sinusoidal pattern. We want to also look at showing the relationship of climatological indices and cosmic mixing ratio. So comparing the Arctic oscillation, the Pacific decadal oscillations, and some of those. That might give us some insight about what other climate indices can we use to get a better understanding of what we maybe can expect and get some more predictability of it. And then this is something I'm actually currently working on right now, is building on what we have with WRF right now by adding Cosmic 2 data simulation, adding sea level height anomalies, and sea surface temperature anomalies to get the full picture of this. I like to give a few acknowledgments. The study was supported by the NASA MUREP grant with the grant number there, and the Center of Applied Atmospheric Research and Education at San Jose State University. I would like to also acknowledge my advisor, Dr. Sen Chow, for all the help he's given me with discussions and talking about what we want to do with this research. Also, Doctors Ying-Hwa and Zhiquan Li are some NCAR scientists that I had some few really good suggestions and discussions with those two scientists, and we really appreciate that. So without further ado, thank you. If you have any questions, please contact us. I have my email right there at plus is my advisor's email, and we would like to hear from you if you have any questions. Thank you.